Looking at section 3.5, the last section in chapter 3, we're going to look at some exponential growth and decay and then doing some modeling of data. So we are going to look at model exponential growth and decay, use logistic growth models, use Newton's law of cooling, choose an appropriate model for data, and express an exponential model in base E. So the first one we have is looking at what exponential growth and decay looks like. So it says that the mathematical model for exponential growth or decay is given by f of t is equal to a sub o e to the kt, or a is equal to a sub o e to the kt. It tells us that if k is greater than 0, the function models the amount or size of a growing entity. So if you're looking at your exponent of k, if k is greater than 0, it's going to grow. If k is less than 0, the next part talks about less than 0, it's going to end up decaying. Well, if it's less than 0, that means it's negative. And if you think about a negative exponent, it flips to the other side of the fraction bar, which makes it into a division. So if an exponent is negative, it really makes it into a division, which means we're going to get smaller, we're going to decay. So back up to that first one. So if our k was greater than 0, we have a growing entity. It said a sub o is the original amount or size of the growing entity at time t is equal to 0. So from the starting point, t equals 0. It says a is the amount at time t, and k is a constant representing the growth rate. So that k value is talking about the growth rate. If k is positive, it's going to grow. If k is negative, it's going to decay. So same type of information on that next bullet. When we have our decay, a sub 0 is still the original amount or size of the decaying entity at time t is equal to 0. A is the amount at time t, and k is the constant representing the decay rate. So in terms of the two functions that we have graphed, if we are looking at our exponential growth, they have our a sub o is starting at some value, and then it's going to increase as time goes by. The other one we have, our exponential decay, is we are going to start somewhere higher up in terms of what we're starting with, and it's going to decrease as time goes by. Kind of makes sense. You grow or you decay. You get bigger or you get smaller. So let's look at an example. It says in 2000, the population of Africa was 807 million, and by 2011, it had grown to 1,052 million. Use the exponential growth model, a is equal to a sub o e to the kt, in which t is the number of years after 2000, to find the exponential growth function that models the data. So we need to go back and see what information we have. We're starting in the year 2000, and they're talking about by the time we get to the year 2011. That means how much time has gone by. Well, t is going to equal 11. It's been 11 years since 2000 if we're talking 2011. It then tells us that in 2000, at the starting point when t was 0, the population of Africa was 807 million. So that's our initial amount. That initial amount is going to be that a sub 0. And by the year 2011, which gave us our t equals 11, it had grown to 1,052 million. So that's going to be our a value. So we're going to use the exponential growth model. A is equal to a sub o e to the kt, in which t is the number of years after 2000, to find the exponential growth function that models the data. So we need to eventually write out what that equation is going to look like, but we're going to fill in what we have from our example and see what else we have left over to solve for. So our a value is going to be that 1052. That's equal to our a sub o of 807. E raised to the kt, well, the k value is what we don't know, so that's what we're going to end up solving for. So we're going to have k times our t. We said t was going to be 11. So we need to solve to figure out what that k value is in order to write out our function or our model of this example. So let's start solving this down to try to figure out what could that k value be. So if I want to get k by itself, I need to get rid of that 807 first. So we're going to divide by 807. So I'm just going to leave this as a fraction for now and do one big calculation later. So that 1052 divided by 807 is going to leave us with e to the k times 11. I'm going to write that as 11k. My algebra mind does not like k times 11. From here, I need to solve for the exponent, which means we need to take the natural log of each side in order to cancel out, or to be able to solve for that exponent. So that means we have ln of 1052 divided by 807 is now going to equal the ln of e to the 11k is just going to leave us with our 11k. And now if I want to get my k all by itself, that means we have to divide by 11. And I divide by 11. So k is going to equal this really, really, really ugly, be careful how you put it in the calculator calculation. So we have an ln of 1052 divided by 807, and that whole thing has to divide by 11. Let's see how good, bad, or ugly our handy dandy calculator helps us out. All right, I need the ln of 1052 divided by 807. That is going to divide by 11. So I end up with a k value of 0.024 is just going to leave us with, and then the one behind it, we'll call this a 0.024. I don't want to just call it a 0.02 because that 4 is kind of getting a little high over there. Almost to like a 0.3 then. So we're going to rewrite our model. Our model means that we have an equation. So we're going to go back to kind of the original information that we have. We're going to have an A is equal to, in general, A is equal to. That 807 is still going to be that initial amount, but now we're going to have E raised to our K value of 0.024, and then we're going to have our T time. So our final model is that really ugly looking thing, and we're going to use that really ugly looking thing to continue on with that example. So I'm just going to rewrite this down here because I'm going to need it to reference it again. So now it had in 2000, the population of Africa, still 807 million, and by 2011 it had grown to the 1052. We used the exponential growth model, A is equal to A sub O to the E to the KT, in which t is the number of years after 2000, to find the exponential growth function that models the data. That's our function. So now it wants to know by which year will Africa's population reach 2,000 million or 2 billion. So we want to figure out by which year our unknown is going to be time, how much time is going to go by, where we're going to end up reaching 200 million, also known as 2 billion. The reason why they wrote that as 200 million is because it initially referred to Africa in terms of millions. So that's why we're leaving it as millions and not taking it to the billions or the 2 billions. All right, so from here, we're going to take our equation and we're going to plug in. So 2,000 is going to be, what are we going to end up with for that A value? So we're going to have a 2,000 is going to equal our 807. We have e to the 0.024 t, because t is now what we're solving for. So now we need to solve this down to get t by itself, very similar to what we had just done to solve for the k value. Start by dividing by 807, divide by 807. So that means we have that 2,000 divided by 807 is equal to e to the 0.024 t. Now, in order to solve for that exponent, we have to take the natural log of each side. That's going to allow us to have our ln of 2,000 divided by 807 is now going to equal our 0.024t, right? Because the ln of e cancels that thing out. So now we can solve to get t by itself by dividing by our 0.024. So we need a little handy dandy calculator again. Let's see. It didn't open the way I wanted, sorry. There we go. So now we are taking the ln of 2,000 divided by 807. Oh, it picked up on a little. ln of 2,000 divided by 807 that we then need to take and divide by 0.024. So we end up with 37.8. So that means t is going to equal 37.8, which we could probably go ahead and round that up to a whole number of years. And it says by the year what? Well, if we're going to estimate that that's about 38 years, plus our starting point of 2000, that means that we're looking at the year 2038 for Africa's population to reach that 200 million or the 2 billion. We're going to do another example very similar to what we just did. This one takes us to a little bit of chemistry. This one talks about the half-life of strontium-90 is 28 years, meaning that after 28 years, a given amount of the substance will have decayed to half the original amount. It wants us to find the exponential decay model for strontium-90, or however you say it. If you want to look it up, Siri could probably tell you better than I can. Not a word that I use on an everyday basis. So obviously a chemical element, you could probably find it on your periodic table of elements. Maybe you've heard of it before. All right, so we are dealing with a half-life. So if we have a half-life, no matter how much I start with, I'm going to end up with half of it in 28 years. That's what that's telling us. So whatever our initial amount of A sub O is, if we divide it by 2, that's going to give us our A value, right? How much we're left over with. So if you think about it, that A value is going to be half of whatever our A sub O value is. So if A sub O is 1, A is going to be a half. If A sub O was 100, half of 100, you'd have 50. So we are just going to refer to that A value as a 1/2. So a half-life is just going to be the number 1/2. And the A sub O, we're just going to call that one amount of this chemical element that we're dealing with. So in regards to setting up this problem, we're going to have an A value of 1/2. That's going to equal the A sub O, we're going to just call that a 1, which means that we're just going to have an E to the KT. Well, they gave us some other information. They told us we have 28 years, so that's a T value of 28. So we have a K times 28. And now we're ready to solve it down. Take the natural log of each side. So that means we're going to end up with ln of 1/2 is equal to, we're just going to have a 28K, and we can get K all by itself by dividing by 28. So all I need to do is plug that into my handy dandy calculator. I know I should probably just keep it open, but it shrinks the screen down so much. All right, if I take the ln of 1/2 and I divide that by 28, I end up with a negative, which think about it, if we're decaying, what type of exponent should we have? We should have a negative, right? A negative 0.02475. Let's call it 248.0248. And if we were to go ahead and write out what that model is, maybe I can keep that just open there. You guys can still see okay, hopefully. All right, if we were to write out what that model looks like, that means in general we have that A is equal to A sub O, whatever initial amount that I plug in. We're going to have that E to the negative 0.0248, and then we still need that T value for time, how to kind of squeeze that in. Now we're going to use that for one last piece. So our model that we had, the same exact thing that we just had, A sub O, E to the negative 0.0248T, is it wants to know if there were, or if there are originally 60 grams, how long will it take for the strontium-90 to decay to a level of 10 grams? So they want to know if our initial A sub O is 60, how many years, how long, we want to know T is equal to what, will we get to 10 grams, which is going to end up being that regular A value. So if we take our equation and we plug things in, that means that we'd end up with our 10 is equal to our initial amount of 60, E to that negative 0.0248 T. We're going to solve for T. So we're going to divide by 60. So we'd have a 10/60th is equal to E to the negative ugliness. We need to take the natural log of each side, which means that we'd have an ln of 10 over 60. If you want to call that a 1/6, I don't like 10 over 60. My math brain says, ugh, right? It's a 1/6. Let's go ahead and simplify that down. ln of 1/6 is going to equal that negative 0.0248T. And then all we have to do is do that division by that ugly, ugly, ugly decimal. So that means we are going to have the ln of 1/6. Let's see if I can't. Nope, it's not going to let me do it. All right, ln of 1/6. We need to take that and divide it by our negative 0.0248. We end up with 72.24. So T is approximately 72.2, I guess, 5. All right, because that 8 will make that 4. Go to the next number, round up. So it will take about how many years? Well, it's going to take about 72 years for that 60 grams of strontium 90 to decay to a level of 10 grams.